Q.Ant takes a giant step toward commercializing its photonic computing technology, how this tech could be used to cut cost and energy consumption associated with AI. A tunable semiconductor laser could replace existing systems with a smaller, more affordable option. How it uses a series of ring-shaped lasers to get the job done and the luminary figures behind the breakthrough. And a portable device that can identify oral cancers and treat them. Why this system could change how photodynamic therapy is accessed around the world. These stories and more on Photonic Spectra Now. Photonic Spectra Now is brought to you by Thorlabs, pioneering photonics technologies to accelerate research and development. Visit thorlabs.com to learn more. Hi, and welcome to Photonic Spectra Now, covering your top headlines in the world of photonics. I'm Joe Kaczynski, a senior editor with Photonic Spectra. Q.Ant, a developer of photonic processing technologies, has raised more than $72 million to advance the commercialization of its photonic processors for AI and high-performance computing. That money comes from investments in a Series A financing round. The future rollout of Q.Ant's light-based processor could address the rising energy and scalability demands driven by AI. Built on thin-film lithium niobate, officials with the company say these processors can integrate into existing data centers with 30 times the energy efficiency, 50 times the performance, and up to 100 times the capacity. Systems and Thales are announcing a new collaboration in laser-driven particle acceleration. The pairing will combine Tau's ultra-fast laser plasma accelerators with Thales high-peak power solid-state lasers. A Thales laser has already been installed in Tau Labs' Carlsbad, California location. Officials from Tau say the work done there will accelerate research and development in areas such as spacebound electronics, advanced X-ray imaging, and biomedical applications. A research team in California says it has successfully integrated indium arsenide quantum dot lasers monolithically on silicon photonics chiplets. These monolithically integrated lasers are more commercially viable and can be manufactured in a standard semiconductor foundry. The scientists were able to overcome coupling loss with the pocket laser strategy for monolithic integration, a two-step material growth arrangement, and polymer gap fill approach that minimizes optical beam divergence in the gap. This PIC technique could work for a range of chip designs without needing major modifications, offering flexibility to manufacturers. A research team from Harvard and Vienna University of Technology has developed a tunable semiconductor laser. The work, co-led by Federico Capasso and Vinton Hayes, led to the creation of a laser that can produce multiple commercially relevant wavelengths while eliminating the moving parts that often raise the cost of such a device. This system consists of multiple tiny ring-shaped lasers, each slightly different in size, all connected to the same waveguide. By adjusting the electric current input, the laser can smoothly tune between wavelengths. A new method of dark state control could expand quantum dot use in quantum applications. Scientists from the University of Innsbruck have devised a way to optically access and manipulate dark excitons and quantum dots using a laser and an external in-plane magnetic field. Researchers say this technique could open up new opportunities for the control of quantum memories and the generation of entangled photon pairs and quantum dots. And a new compact device could help detect oral cancer and treat it through photodynamic therapy. Researchers across several North American universities and hospitals sought to build a low-cost handheld system while looking into the prevalence of oral cancer in South Asia. By using a smartphone-coupled intraoral probe, this device can capture images to pinpoint cancers. It also includes laser diodes that can activate a compound that accumulates in cancerous tissue after a drug is administered. When exposed to light, this drug produces reactive molecules that can destroy cancer cells while sparing healthy tissue. Do you have news you'd like to share or suggestions for our team? You can send any story tips, questions, or comments to video@photonics.com. Give us a like and click the subscribe button in the corner for all the latest videos from Photonics Media, and be sure to follow us on all your favorite social media platforms. Remember, you can always find more details on these stories and everything else happening in the industry by going to photonics.com. I'm Joe Kaczynski, and thanks for watching.